We have seen that we can linearize the power flow equation using first order Taylor approximation, but we can do that a bit in a more powerful way by doing it iteratively. This is called sequential linear programming. The names, one of the difficulty in engineering is that the names are sometimes misleading. What is sequential linearization of the load flow equations. Whether it's linear programming depends, of course, on the objective function. If you have a quadratic objective function, it will not be linear programming, but the same idea applies. Most of the time it is used when everything is linear, hence the name. So assume I have to minimize a cost that is expressed in polar coordinates for the electrical state and rectangular coordinates for the power injections, which is a very common case. We know how to linearize the power flow equation if we know a value, which here I call pk qk, by using the Jacobian of the load flow as we have discussed before. Now, one way to solve the OPF is to do the following. So let's look at one. We do it iteratively. That means we try k times, so from 0 to k max, typically depending on how fast your program goes. K is only limited by the time budget that you want to give to your optimizer. In one iteration, you use the result from the previous iteration. For example, in the first iteration, you use an approximate solution of your OPF. For example, the DC-OPF. The DC-OPF will give you V0, which is 1, theta, which are the optimal angles, the injected power that are the optimal values given by DC-OPF, and Q is ignored by DC-OPF, so we set it to 0. So that gives you a starting point. Like we have seen in the previous examples, on the 3-node example, we have seen how to solve it with DC-OPF. Your DC-OPF solution is, of course, not a true load flow solution. So the first thing you need to do is first transform what you had into an exact load flow solution. There's multiple ways to do it. You can take P0, Q0 and do a load flow, or you can do it the other way around, which is numerically simpler. You take the V0 that you have, the theta 0, and you compute the resulting P and Q, which will not be the P and Q that you would like to implement, but that will give you something that is an exact load flow solution. So you will find P0 that is slightly different because now there will be the losses incorporated, and there will be the Q that are not due to the node injections because you set Q to 0, in the original solution, but that are nodes that are due to the lines, for example. Then in the first iteration, you will solve the following problem. Find the optimal control variables, the optimal state, the optimal power injections, assuming that the linearized load flow equations are exact at this point that I have here. So I take V0, theta 0, and I replace the load flow equation by PQ equal P0 Q0 plus the Jacobian times the difference in V and theta, and other linear constraints that I may have on V theta. Since they are linear, I don't need to worry about them. So I will solve an approximate OPF. I will not solve the original OPF. I will solve an approximate OPF that has the benefit now of having linear constraints. So if the objective function is linear, then that will be a linear program. If it's convex, then it will still be a convex problem, so I can probably solve it. Now, I've solved an approximate OPF, and what is approximate are the grid equations. The power flow equations are approximate, which means that the solution that I will find is not physically feasible. The relation between the P and the theta are not exact. So what I will do is I will change my solution to make them exact. For example, by taking the electrical state that I have found and transform it to be exact. There will be an error that will be small if the optimal point is not very far from the previous point. which is probably the case already at step 1, because we've seen that the DC approximation finds, at least in the kind of grids to which it applies, it finds a solution that is not far from the AC-OPF solution. So that will be probably already close, but there will be a small correction to do. And then you iterate, you correct again. So at every step of the iteration, you have replaced the load flow equation by a linearized set of constraints that are exact at the previous point that you had found. Whether this works or not in general, we don't know. As far as I know, the theory is not closed on that, but practically, in many cases, it does work. It works in the sense that if I do that iteratively, I find a point that provides convergence. So that when I correct here, of course, the PQ that I have are changed a bit. So the next iteration, I found another PQ. And if this thing converges, the optimal point that I've found converges to something that doesn't move. So if that happens, then we say that the sequential linear programming heuristic has converged. Practically, for a large class of problems, it works, in particular if you're not operating at the boundary of the feasibility of the grid. For example, let's examine what this gives if we apply it to the voltage control problem we've seen before. The very first instance of the problem is the one that I've explained before. We say I wanted to control the voltage by computing the set point of some of the generators that I can control. I can reduce, for example, their amount when the uncontrolled generators, the PVs, are large. Or I can also reduce the power injected by the PVs by curtailing them. Of course, the owners of the PVs will not be happy if you reduce their production, but it is envisioned that this is a way some grids will work in the future. In fact, there is a plan for Switzerland for 2035 to have a massive deployment of solar energy, solar electricity, that will be dimensioned for the winter. So we will, in winter, have enough solar energy, of course complemented with other sources of energy, particularly from hydro, which means that in the summer we'll have excess energy. So in the summer, we will need to curtail the PVs. We'll need to curtail for reasons of voltage control, also perhaps for other reasons due to direct control of the power, because we're not able to sell it to anybody. So this will happen very frequently in the future. We've seen the first way to do it, which is to say, I am operating right now at this value, P hat, Q hat. I want to decide which next value I will give to my generators for example, the next minute. Then I solve this OPF, I obtain value PQ, and I implement them. That's one way to do it. It's not sequential linear programming. When I do this, I compute a value of V, which is not the exact value. It's the value of V that is predicted by this approximation. So it will be okay. But if we want to improve it to have a more accurate control, we could do sequential linear programming. So we'll do exactly the same here. Instead of doing it once, I will do K times, K max times. I will minimize my cost function, which includes the voltage penalty, subject to the linearization I have done at the previous step, and then I will iterate here. If I do this, I will converge to something that will be exactly feasible. Thus, if this converges, and in practice, you will see in the lab you will need to implement 1NS, you will see that those two things converge. In practice, because when we're doing voltage control, we're deviating a bit from the current state, so it's very likely that it will work. If it doesn't converge, you will still always provide something that is an exact solution of an approximate solution of the problem. So intuitively, it is not very bad. So even if it doesn't converge, because in this equation here, we force the exactness of the load flow solution, we will find an exact load flow solution. Perhaps not the exact solution to the optimal problem, but certainly an exact load flow solution, which means the voltage that we compute at this operating point is exactly the voltage that will happen. Whereas here, it might not be exactly the case. Voila, a quick recap. First question, two statements, which of them are true? I close in a few seconds. And the exact solution is B. It satisfies the AC power flow equation exactly. That's the benefit of SLP. However, it is not necessarily the true minimizer of the AC-OPF problem. Of course, if there would be a linear way to obtain a true minimizer of the AC-OPF problem, that would be wonderful, but that's not the case. Similar questions now with DC-OPF. I close the poll now. And the vast majority says D, which is correct. The solution is not a true minimizer of the AC-OPF problem. It does not even satisfy the AC power flow exactly. So because it satisfies the AC power flow exactly, the DC power flow exactly, which as we've seen are a bit different. They ignore the losses, and therefore it is certainly not a true minimizer of the AC-OPF problem. So that's the difference between SLP and DC-OPF. DC-OPF is of course much simpler. It always works. It's always guaranteed to converge. There's no convergence. It's a one-step problem, but it does not provide a true feasible solution of the physics of the grid. Voilà, that's for the approximations of the OPF. The last thing we need to discuss is the marginal prices. OPFs are used in energy markets and in grid control for, as I said, a large number of purposes. One of them invariably produces marginal prices, and this is used in energy markets to obtain, for example, locational marginal prices. We have seen on the examples of the grid that I've shown a few minutes ago that we had sometimes a price, the marginal price at every node, which is the price we would need to pay to provide the generation that's required by an increment of generation in one node. So this is used, for example, in market liberalizations to try to find prices of electricity that take into account the constraints of the grid. We've seen, of course, that the prices are very different when the grid is weak. We've seen two examples of a grid and of a weak and strong grid. The first example, when there was a strong limitation on one branch, we saw that the prices were very different. So to understand this, we need to recap a few things on duality of optimization. Again, the goal of this course is not to go in depth into duality. So what I will do instead is give you cheat sheets to everything you need to know about duality for this context and probably for many other contexts. Duality is a very rich topic, which is not so complicated, except for the notation. So I've looked in my life at many textbooks on optimization, and there's only one that's really good, in my opinion. It is the one by Boyd and Vandenberghe. So it's better to stick to their notation. The trick really in understanding optimization, Lagrange duality, and all that stuff is really making sure we have the correct notation, because it's subtle. There are sometimes little details that are very important. Like, for example, whether a Lagrange multiplier is positive or negative or does not have any constraint. So my approach here is to stick to the best textbook I've found, and this is this one. So in particular, this textbook uses a unique form for all optimization problems, which is this one. An optimization problem is always a minimization of a function f subject to constraints that can be inequalities or equality. And if they are inequalities, they're always less than or equal to 0. And if they are equality, they're equal to 0. So of course, if you have any other kinds of inequalities, you can always transform in this form. And if you have a maximization problem, then maximizing f is equivalent to minimizing minus f. If you minimize minus f, the resulting thing, you take the minus of that, and that will give you the solution to your original problem. So that applies to minimization or maximization. But that's the standard form used by Boyd and Vandenberghe. By the way, Boyd and Vandenberghe have a book, a textbook that's online. That's why also it's a good reference, and I give a reference to that on Moodle. Some convention, such a problem, we say minimum. In fact, what we want is to find the inf. The minimum might not be achieved. In particular, it might be infinite. We say that the problem is feasible if the set of constraints is feasible. So there is only one point that satisfies the constraint. Be careful here, there's a small subtle detail. There is an implicit constraint which is called the domain of definition. The domain of definition sometimes is obvious. For example, if I have a function of x that is 1 over x, then x is equal to 0 is not possible. So the domain of definition will be x different than 0. But the domain of definition can be anything that you choose. So in fact, you can put constraints into the domain of definition. Or you can put them here. It's up to you. It will give different duality statements depending on what you do, but both are possible. So we say that the problem is feasible if there is at least one solution to x in capital X and satisfying all the inequalities and equality here. If your problem is not feasible, then the optimal value, the solution of that, is said to be plus infinity. Plus infinity, that's weird. Why is, well, that's a convention because the neutral element with respect to the minimum is plus infinity. If you take the minimum of A and B is plus infinity, then it's equal to A. So it's just like the sum of an empty set is 0, the product of an empty set is 1, the mean of an empty set is plus infinity. We always take the neutral element of the operation. The problem is unbounded if there is at least one feasible point, but in fact there are many feasible points, and f can be as small as you want. So in fact, there is no minimum. There is an infimum, which is minus infinity. In that case, we will say that the solution of the problem is minus infinity. So I give those conventions because all the statements that we will make include these cases. The main thing that we're interested in is introducing the dual problem. That's an extremely powerful thing in optimization. We will see repeatedly. So it's important to do it well. So I have a problem defined in this form. Here, sorry for the notation. The domain of definition now is called D. So those are all the constraints on X, right? Then, as you probably all have already encountered, the Lagrangian is a function of the X and additional variables, which are called the multipliers, where we take the constraints. So we add lambda I. For every constraint, we have one multiplier. So a constraint is a numerical thing. Here, fi is a function that returns a number. It's not a vector. So if it's a vector, if I have 10 inequalities, I will have 10 Lagrange multipliers corresponding to inequalities. So I take this, I multiply every inequality by lambda I, and similarly, every equality has another multiplier. And the multiplier that corresponds to inequalities must be non-negative. That's the convention if we have this representation here. Now, why do we use the Lagrangian? Well, that's a trick to remove the constraints. Solving optimization problems that are not constrained is easy, at least is doable, if the optimization function has a differential, if we can compute the Jacobian matrix, because the gradient, sorry, because a point that achieves the minimum, if it's convex, for example, there is only one point that achieves the minimum, and it's obtained by setting the gradient to 0. So setting the gradient to 0 can be done by a number of methods, Newton-Raphson, etc. So that's the idea. The idea behind duality is that we want to remove the constraints. So we remove the constraint by associated to the original constraint problem an unconstrained problem, but there is one problem per set of values of the Lagrange multipliers. And so what we minimize, instead of minimizing the objective function, we minimize this plus this combination of the constraints. So the classical interpretation consists in saying instead of taking hard constraints here, we put them in the form of penalty. This should be negative. So if it is strictly negative, we put a penalty multiplied by lambda I. So we pay a penalty for not satisfying the constraint here, and similar here. So for every value of the vector lambda and nu, we have an unconstrained problem here, which we can minimize. Now it's easier. So the solution of this optimum problem, we don't care about the x, but we care about the value. And the value here is called g of lambda nu. For every lambda nu, there is an unconstrained problem. I solve this unconstrained problem. I obtain a value, which may be infinite if the problem is infeasible, minus infinite if it's non-bounded. And the dual problem is maximizing the value of this unconstrained problem. Subject to what are the constraints? The constraint on lambda are given here. On nu, there is no apparent constraint, but there is a set of constraints. The constraint is that the multipliers here must be such that this problem is bounded from below, which means that the minimum is finite here. It does achieve a finite minimum. So that's the domain of definition of the function g. So that gives us the dual problem. It seems a bit magical, and I don't have time to explain why, but believe me, that is the correct way to look at things. Then there is the well-known duality result that says that if we solve the dual problem in the space of lambda nu, we obtain a value, d star, that is always less than or equal to the optimal value of the original problem. And in many cases of interest, they're equal. Now, if they're not equal, we say there is a duality gap, and the duality gap is the difference between the two. Of course, in reality, we don't care so much about the value of the optimization problem. What we care is what are the variables that achieves the minimum. So the duality result, in that sense, is not exactly what we want. What we want is to solve our original problem. So the very common approach, there are two very common approaches. One is the saddle point, the other one is the KKT conditions to solve constraint problems. The first one, the saddle point, consists in solving the optimal problem with unconstrained problem with multipliers lambda and nu. So that gives us a value of x. Now, for every lambda and nu, I find an x star that in fact depends on lambda and nu. And then I look for lambda and nu such that the resulting solution is feasible for the original problem. Feasible for the original problem, that means satisfies the constraint that I've dropped when I've constructed the unconstrained problem here. So the idea is very simple. I remove the constraint by hypothesizing, assuming some values of lambda and nu. I obtain some x, and then I compute the values of x and of lambda and nu such that the x that I have obtained satisfies the constraint. So that's very simple-minded. The magic thing is that it works. If we do this, we obtain values of lambda and nu and of x that are both solutions of the optimal and the dual problem. We might think that we are primarily interested in finding the solution of the optimal, but we will see that the dual variables also have a physical interpretation. So in reality, we are interested in them. This will work only in cases where strong duality happens. Because if this happens, then strong duality must happen. I said that we solve for x that satisfies the feasibility constraint of the original problem. There is a small subtlety here, which is called the complementary slackness condition. The complementary slackness condition, remember that the constraints of the original problem are inequality constraint here. Fi is inequality constraint. And here, a solution that we obtain must satisfy the following condition that are called complementary slackness. If the lambda that I have is positive, so if the multiplier is non-zero, then the constraint must be satisfied with equality. Or otherwise, if Fi satisfies the constraint strictly, the multiplier is zero. That is related to the economical interpretation of the Lagrange multiplier. If the multiplier is non-zero, is zero, that means in fact that this constraint was not binding. That means it was the x, the optimal x, satisfied Fi of x strictly less than zero, which means that there is some slackness, there is some margin in Fi. So we add those constraints in, and if we apply them, then what I said is verbatim true. This is one method called the saddle point interpretation of the Lagrange duality. Another concrete method for solving it is related to solving the zeros of a gradient, which is called the Karush-Kuhn-Tucker condition. It works only if we can assume that the problem is convex and that all functions are differentiable. It's not always the case. For example, if you have a max, it's not differentiable, but we've seen also that we can remove a max. Then the conditions are like before. I look for a point x and multiplies lambda and nu that are such that x is feasible, such that the complementary slackness conditions are true, and then such that these conditions here, which are the true Karush-Kuhn-Tucker conditions, are true here. Essentially, those are conditions that say that are obtained when we set up the gradient of the Lagrangian to zero. Remember that when we have the Lagrangian, we have removed the constraints. So if the domain of definition is open, then an optimizer must satisfy that the gradient is zero. And the gradient is zero means exactly this here. Same thing here. If we find values of x star and lambda star that satisfy this, then we must have found the optimal of everything, of the optimal and the dual. So if we try to have the Karush-Kuhn-Tucker conditions for anything else than lambda nu that are the correct lambda nu, it will be impossible. And of course, it works only when strong duality holds. So this is numerically perhaps the most widespread method for solving constraint problems. The first one, saddle point, is used for reasoning in theory. This one is for reasoning theoretically. I mentioned that those two methods work only when strong duality holds. So strong duality, it's interesting to be able to predict when strong duality holds. So a well-known result is that strong duality holds when constraint qualifications hold and the problem is convex. Most convex problems are in this case, but you can find weird cases that are not in this case. In particular, one constraint you must have is that the problem must be feasible. You must say, yeah, of course, a problem is feasible, but if you write a problem in general, a problem might not be feasible. If it's not feasible, duality might not hold strongly. And you need additional conditions. For example, if all equality constraints are affine and inequality constraints are affine, that means linear plus constant, which we will in practice most of the time have. So for us, if all the constraints are linear, and the problem is convex, so the objective function is convex, strong duality holds if the problem is feasible. That's the take-home message. And if strong duality holds, that means that the Karush-Kuntuker condition will work, and also the saddle point will work. Voila. So that was everything you need to know about duality in 15 minutes. Of course, it's impossible to digest all those results in 15 minutes. If those results are new to you, then what I encourage you to do is to do part 1 of the lab. You can do it immediately now. Of course, you have another lab to finish, but when you're done with that, you can start that. Part 1 of the lab is a pencil and paper exercise where I ask you to apply all these methods on a small, nonlinear, but convex problems, and you will see how concretely those methods unfold, and then you will be able to understand the different statements I have made here. If you are familiar with this, then you can use this as cheat sheet to verify the things you've learned in other lectures. But the main reason I was introducing all this is shadow prices. So if I have a problem where strong duality holds, so typically it's convex and not too nasty, for example, linear and feasible, then if, in addition, the cost is differentiable, which is not always the case, but very often is, then the optimal cost of this problem, I may formulate it as a function of the right-hand side of the inequalities. Of course, here I've cheated a bit. So I said I use the standard form. So the standard form will be 0. Of course, I can very easily express it by saying fi of x minus ui is less than 0. So if I have a problem that I can put in this form, so which means the function for the inequality is a fixed function minus an offset, and this offset I call it ui, and same thing for the inequalities. Then I can ask the question, so for every u and v, I have a problem, and the problem has an optimal cost. And I can ask the question, how does the optimal cost vary with respect to the value of the constraints here? And the answer is, if the cost is differentiable, the derivative of the cost with respect to ui is minus the Lagrange multiplier that corresponds to that. Of course, when I say the Lagrange multiplier that corresponds to it, I have to put it in standard form, which means the standard form will be fi minus ui. Similarly, for the other one here, I will have dc over dv, which is minus nu here. Why is that interesting? Well, it has the interpretation of a shadow price. If this constraint expresses a resource, we will see in a minute what that means. But assume you have a constraint and you can buy, by putting money onto the table, you could increase the value here. If you increase the value of ui, you have more freedom for you. You're less constrained, so you can improve your cost. If you have fewer constraints, if you're less constrained, then you have a bigger space and the minimum can be smaller here. And the answer is, if I can add some small quantity, epsilon I, to the ith constraint, which I interpret as a resource here, this will decrease the cost by lambda I epsilon I. So if I could buy this augmentation of the constraint, if I'm offered to buy it at a price that is less than lambda I, then I should buy it, because my cost will be reduced by lambda I epsilon, and I've paid less than lambda I epsilon. So if I'm optimizer, it's rational to buy this increase of the constraint whenever the price is less than lambda I. Conversely, if somebody offers me to buy, but at a price that's larger than lambda I should not buy it because the net benefit for me is negative. So we can interpret lambda I as the hidden cost of this constraint, which is also called the shadow price. That's the implicit price, the price at which a rational optimizer would be willing to buy an increase of the constraint. So that's the generic interpretation. Now let's return to the OPF, which is our topic for today. If the OPF is put in the form of a convex problem, such that a fine duality, strong duality holds, for example, with a fine inequality and equality constraints of this form here, then the locational marginal price at cost 1, at node 1, for example, is the partial derivative of the optimal cost with respect to the demand at node 1. Now, the parameter ui here, in general, will be a function of all the parameters of the problem, in particular of L1. So if I take the derivative of C with respect to L1 by the total derivative formula, I should take the derivative of C with respect to ui, which is minus lambda I, multiplied by the derivative of ui with respect to lambda I. So that is the formula for the marginal price, the additional cost I will need to pay if I increase by a small quantity the demand at node I. So this is called the locational marginal price of demand at a given node here. Again, a function that plays an important role in electricity markets because that tells us exactly where the price should settle if we do a price that depends on location. Let's return to our example. To simplify, I do it for the DC-OPF only, not for other forms. We can do it for SLP. This is typically what is done when we really want to be very accurate. Let's do it for DC-OPF. So that's the DC-OPF problem I have. So how many constraints do I have? I have here 1, 2, 3 inequality constraints. So I have 3 multipliers that I called new. And how many inequality constraints do I have? I have 1, 2, 3 times 2, because this is absolute value. So this is plus and minus. So each of those is 2 inequalities. So I have 6 inequalities here. And here I have, again, why do I have 16 in total? Here I have 6 inequalities. Then I have 3 times 2, 6 inequalities for the 2 times 2, 4 inequalities. Theta 1 is 0. And here I have, for the generation, I have 2 inequalities times 2. So in total, I have 16 Lagrange multipliers. So that's hidden behind this. If I look in detail at the MATLAB solver and I ask for all the multipliers, it will return to me 16 inequality constraints multipliers and 3 equality constraints multipliers. Here's the values that are returned by MATLAB. Now, if I apply the formula I had before, what is the locational marginal price at node 1? Then it's DC over dL1. I need to look at what is the derivative of all the parameters, all the right-hand sides that are everywhere with respect to L1. Now, there's only one constraint here, so there's only one multiplier that's involved, and the partial derivative with respect to L1 is simply minus 1. So the marginal price is minus nu 1, which is this value that I've obtained here. So the Lagrange multipliers here are in fact exactly equal to the locational marginal prices here. Here I have listed, for curiosity, all the Lagrange multipliers that are returned. We see that they're all 0. Those are all the ones for inequality constraint. They're all 0 except 2 of them here. Which leads me to my next quiz. At the optimum, which of the resources, at least in the DC-OPF, are at their limits? I close the poll in a few seconds. And the majority says A, which is the correct answer. Here, we simply have the list of all the Lagrange multiplier. We see that there is one that is the only ones that is non-zero are the ones at which the constraints are binding. This is the complementary slackness conditions. We see that the two constraints that are binding are P23 and G1 max, which means we hit the max limit of the first generator, and we hit also the power flow limit in the DC approximation on the line 2,3, which is this line here. So this is what the multipliers tell us when they are non-zero. We can also verify the interpretation of marginal cost by simply resolving the problem by adding a small quantity. Here I added 1 and I looked at what is the optimal cost. We see the increase in cost, so we see that the marginal cost is 60 as predicted by the value of the multiplier here. Last quiz of the day. At which price would you be willing to buy an increase in capacity of the line 2,3? We've seen that the line 2,3 is limiting, at least in this DC approximation. At which price would you buy an increased capacity? I close in a few seconds. And now the majority says A, but the correct answer is C, because the majority was influenced by my previous statement where I showed timeout. Here we need to look at the value here. Here, that's the value here. When we multiply by the Lagrange, by the differential here, the marginal cost is given by the Lagrange multiplier associated with a constraint here. That gives us the answer 60. And same here, we can verify by adding 1 megawatt, and we will see, 373, of course, yes. The majority is right, as usual. That was it. Voila, that's it for today. That's the end of our first part of the OPF. Your job for the rest of this module, next week, we will see how we handle uncertainty. So this will be generating a number of very different technical issues. Right now, what you should make sure is that you understand DC-OPF well. If duality is new to you, you should also make sure you understand it well. And with what we have seen, now you are ready to do the first quiz and start already the lab if you have enough time and desire to do so. Thank you very much. Bonne semaine à tous.